system. And yesterday we discussed about this octal number system and how we can convert from decimal to octal, octal to binary, binary to octal, and so on. Today we will see another number system, which is hexadecimal number system. So there was one question yesterday which I tried to answer, that what is the application of octal number system. So there is another interesting application of octal number system, that whenever you have to define binary numbers, if you assume a binary keyboard, a keyboard which has only two keys, 0 and 1, that should have been sort of input device for a binary number. Then if you have to add a binary number which is say 64-bit, then you have to press these keys 64 times, which is really very, very long and hectic task, and indeed can lead to error. Because suppose you have to write down 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, something like this. And even if you miss even a single bit, the whole process is ruined, gone, wrong. So to actually get rid of such hectic process, people design keyboards which are based upon octal number system. So suppose you have a keyboard based upon octal number system. So you press one single key in octal number system based keyboard, and 3 binary numbers will be typed simultaneously. So it will be rather convenient to remember a triplet of binary numbers, like, okay, suppose you have to enter 101, 111, 0011. So you can pick a triplet set and then accordingly get the octal number system. Then on octal keyboard, you can type those numbers which are from 0 to 7. So they are relatively easy to visualize and understand and work with. So that is what is another very interesting application of octal number system. Now talking about hexadecimal number system, as we have already seen yesterday as well. So hexadecimal number system consists of 16 different symbols going from 0, 1, 2, 3 all the way up to F. So in decimal number system, after 9 comes 10. But in hexadecimal number system, after 9 should come A. Then 11 should mean B. 12 should mean C in hexadecimal, and so on. So similar to octal based code keyboard, you may have a keyboard with 16 keys based upon hexadecimal number system, so that if you press a single key in hexadecimal number system or hexadecimal keyboard, you will get 4 bits simultaneously. So what will be those 4 bits? Depends upon what key you press. Suppose you press C, so you should get 1100. If you press F, you should get 1111. So how to design that keyboard can be done with the help of coders, coding and decoding. We will be studying that. But yes, that is the application of, that is one of the interesting applications of these hexadecimal or even octal number systems. So let us first try to understand hexadecimal number systems and conversion from other number systems to hexadecimal and vice versa. So let us, we will be doing more examples so that we can understand things better. So now I give you this number. If you have understood something of a hexadecimal number system, and even from the previous classes, the basics are going to remain same. In hexadecimal number system, the base is going to be 16, or the radix size is 16. So what should this number be in say decimal form? What should this number in hexadecimal number system should be in corresponding decimal form? Yes, please try it. Will you be able to do this? Okay, Jyoti got it 310.214. Tanvi got it totally different. Akanksha as well. Anika, sorry, as well in a different way. Okay. Anshul 310.215. Tanvi and Anika, many are getting, there are two broad categories. One set of students are getting 310.215, other set of students are getting 58.1836. That is really interesting. So how to do this? Here is the detail. So all those who got 58.1836 are correct. So here the base is 16. Okay. Now if the base is 16, the rules are going to remain same. So this, the weight for this is 16 raised to the power 0, and for this is 16 raised to the power 1. For 2 it is 1 by 16. For I mean for this digit it is 1 by 16 square. So what is this number overall? 3 into 16 raised to the power 1 plus 10 into 16 raised to the power 0 plus 2 divided by 16 plus 15 divided by 16 square. What is this is 48. This one is 10 into 1 actually. This is 2 by 16. This is 15 by 16 square. So some numbers are straightforward. 48 plus 10, 58. What is 2 by 16? 2 by 16 is 0.125 plus 15 divided by 16 square will be 0.05859,375, something like this if I didn't do it wrong. I mean 15 divided by, just a moment, okay, 16 square. Yeah, this should be 0.05859,375. And if you add all those numbers, you should finally get 58 point. What many of you have got, but others, those who didn't get it correctly, are you okay now, Anshul? Anshul, are you okay with this? Jyoti? Okay, what mistake had you done? Jyoti, what was the mistake? Jyoti, what mistake you had done? Why you got 310.215? You may type your answer, no problem. If you have a network problem, you can just type it. Anshul, what was the mistake? You also got 310.215. What was the mistake? Okay, so with what number you were multiplying? Sir, वो बस लगा symbol. Oh, either write Hindi or English. ये English में हिंदी नहीं चलना चाहिए. Either you type in Hindi keyboard, that will also be okay. Anyway, ये क्या बोल रहा है? Simple form में बताना है तो वो ही बताए. I don't know what you are saying. Anyway, so I hope you know how to convert from hexadecimal to decimal number system. Let us do some vice versa now. How can we convert from decimal to hexadecimal? Okay, I'll give you this number. How can you get back hexadecimal number system from this? Given that 19.5.5 is in decimal form. So this is in decimal number system. So how can you get it in hexadecimal form? Can you try? Yes, try. Yes, waiting for your response. Five F dot 8. Okay. Let me wait for others. Okay, most of you are getting the same answer, right? Let us see if everyone is getting this. Only few students respond. Many are sitting silently. So please type your response, waiting for it. Okay, almost everybody is getting 5F.8. So 95 would be 5F. And I'm sorry, I missed the remaining part. Yes, it should be 5F.8. So how to convert from a decimal to hexadecimal is also correct. I mean, you got it correct. This is 5F.8. Let us do second one. I mean, one more last practice to convert from decimal to hexadecimal. This is in decimal, 675.625. Try this one, please. Yes, I'm waiting. Yes, please keep on doing. Okay, so most of you got it like 2A3 dot A. So this is the answer. So 675.62 is 2A3 dot A. So I hope you all understood the logic correctly, and that is a good thing. Fine. Let's move further then and try to understand hexadecimal to binary conversion. Again, with the help of examples, we will be understanding this. Okay, let me give you this number. You convert now this number, which is in hexadecimal format, to corresponding binary form. Now let me see how many of you do it really quick. Yes, go ahead, please. Oh, very good. Sir, we have to take 3 bits. That's up to you. How you do is. Oh, okay. 2, A, 3. There seems a trouble with 3. Anshul, 0, 1. Okay, fine. I mean, before I. Okay, let's see the answer. Here is the answer. I hope most of you have done it correctly. Yes. So it will be 2F. So what we have to actually do is, in hexadecimal number system, what is 2? It is a set of 4 binary bits. So 0010 is 2. What is F? It is 1111. So if you press F, something like F in a keyboard, you should get 1111. If you say 9, that is 1001. If you say A, then this is 1010. And then you can just get rid of this gap. So actually this is how this number should look in binary form. I hope most of you have done it correct. That's perfectly okay. Now let's do other way around. Means reverse of what we did. Means let's convert back from binary to hexadecimal. So here's one example. Convert this to hexadecimal form. Yes, any answer? Yes, waiting for your response. I don't think it is that difficult. Yes, I hope you are able to see the screen. Question is clear. Binary to hexadecimal conversion. The number is coming on your screen. Come on. Is it that difficult? I don't think. Am I audible there? Am I audible there? Yes, students. Very strange. Nobody is responding. Pranjal, can you hear me? Anshul. Okay, here is the time for your class attendance. Type your roll numbers. Type your attendance. Now the response is fully coming. And you're not responding for the answer. Very strange. Akriti 29AF. Shubh 29AF. Okay. Tanvi 29AF. Most of you got it. It was that time consuming. How you are converting? Okay, can anybody help me understand that how to get this? How did you get this? How you are converting? Okay, let me show it up. Maybe it is on screen. Yes. So the process is not that difficult actually. What you have to do is you have to take the number from least significant bit. We have to make a set of 4 binary numbers. So we will be having a first set of 4s, this 1111, which is nothing but F. Then we will be having another set of 4s, 0101, right? From here, 0101, which is nothing but A. Then next set of 4 bits, which is 1001, and this is nothing but 9. Then you will be left with 2 bits only, 10. So you have to add zeros to the left to make it complete set of 4 bits, and this is nothing but 2. So the conversion is very simple, and it should not take that long. Maybe there was some problem, technical problem from an internet side or whatever. Well, let me give you another example then. Okay, you do this one. Let us see how well and how fast you do this. I don't think this should take long time. Okay, this is now the question. Yes, please. Oh, Jyoti is saying we all respond. How can you say you all are responding? You can just talk about yourself. But okay, I appreciate your sincerity and assume that all of you are responding. Well, so Kanika is saying this is 0.1EB4. Well, here is the answer. 0.1EB4. The process is same. So you have to choose radix point in case of fractional numbers as a reference. Then from there you have to make set of 4 binary numbers. So the answer to this is 1EB4 in hexadecimal form. Oh, Jyoti, why is it 1D? There is something wrong. It is 1E, because if you go back and see that table, then this 1110 is E. You can go back and look at the table. What is 1110 is E. Okay. So this should be 1EB4 to the base 16. Very good. I hope it is clear. Let us do some more examples, right? Because more we practice, better we understand. Now I am giving you binary form. You get me hexadecimal form. Very good. Let us see how fast you can do. Yes, response. Very good. Tanvi typed. First of all, Tanvi was fastest. Okay. But along with being fast, we have to be correct as well, right? Let us see what is the answer to this. So this is correct, 671.179. Very good. Most of you did it correct. One last example. Okay, do this one. What is this equal to? Again, let us see who is the fastest one. Very good, very good. Anshul is the fastest. fastest one. 2DE.CA6. Let us see if it is so. 2DE.CA6. Correct. Very good. So most of you got it correct. Very nice. So you understood the logic. Okay, one last. This one. Again, let us see who is the fastest one. This is the last one. Last example. Good. Try it. Very good. So this time the first response was from Tanvi. Very good. Let us see if it is correct. 1F1.99A. Correct. So most of you got it fine. Very good. So now let us do some more conversions. Now let us see how to go from hexadecimal to octal number system. Let me give you example. You do it. Apply your mind and so you have to convert this number to octal number system now. Let me see who does it fastest. Oh, some people did it wrong. I mean, the previous example, some people are saying 1F1.994. So cross check. Sonali, maybe you need to check your answer. Huh? So octal number system, okay? You have to convert the given number coming on your screen to octal form. Anshul, not in octal, man. This is binary. I want in octal. Get it in octal number system, 0 to 7. Akriti, how can we get 8 in octal number system? 8 doesn't appear in octal number system. Don't do wrong things to be fast. Take time, because even doing things faster needs time. Okay? Okay, Anika came up with one response. I don't know whether it is correct or not. We will cross check it. Well, let us see. 1, 2, 3, 4, 5, 6. What is this? Number seems interesting. Well, let us see what others are getting. Very good. So this is A7. How we would have done it? Maybe, I mean, the best way to do this is first write down this number in binary form. We will have a set of nibble, a set of 4 bits in binary number system is called a nibble, N-I-B-B-L-E, nibble, and a set of 8 bits in a binary number system is called a byte. Okay, so this we can say nibble. Anyhow, so what we do, we first write it in binary form, then from these we make set of 3 bits, but we have to begin from the least significant bit side. From this side we have to begin. So 3, 3, 3, 3 and so on. Now the conversion will be very simple, right? Because we know what is this, we know what is this, this and so on. So that is how we can convert without taking much time. Whoa, Yashika, so much in hurry, huh? Okay, fine. Okay, let us do another example. Okay, now I again leave it to you. Let us see how fast you can do. Do it correct properly, and let us try to do it as fast as we can. This is the number, convert it. Very good. Waiting for response. No response as of now. Oh, Anshul did it fastest. Let us see. Then Akriti, then Anika. Maybe we can make a list of top 5. Huh? But let us see, is it correct? Almost everybody is getting same answer. So let us see if the answer is correct. 0.577024. 0.577024. Very good. Almost everybody did it correct. Okay, one more. Now, this is other way around. The conversion is other way around. Now I am giving you a number in octal number system, and you are required to convert it into hexadecimal number system. Let us see what you get out of it. Yes, go ahead. 247.36 to the base 8. It's in octal number system. Very good. Most of you got the previous example correct. Can you all switch on your cameras? I just want to see that you are working properly. Have proper sitting place, comfortable place. Very nice, very good. Disha is first to respond. Mohit, very good. Very nice, very good. Keep working, keep working, no problem. That's fine. Mukul, your network now? Mukul? Okay, I am able to see the responses now. Very good. Tanvi was first to respond. Very good. Mukul, can you hear me? Okay, A7.78. A7.78. Well, that's how to convert, right? So what you do is first you write down corresponding binary form, which will be sort of 3 bits each. Then you just make a group of 4 and then get the answer. This is really very simple. You don't need to get into the base, do all those multiplication and all business, multiplication and division business. So the conversion is quite simple and straightforward. So A7.78 to the base 16. Very good. Now let us try to understand how we do arithmetic in hexadecimal number system. How to do arithmetic in hexadecimal number system. One example is, suppose we want to add 7f to the base 16 to a number ba to the base 16. So how we can do that? One thing is, okay, you can try f plus a, then you have to go to the table for hexadecimal number system, because after f will be, I think, next digit. Then you have to find out what is a equal to in decimal. Rather than doing that, you convert this number to binary form, the same number again to binary form, this second one, and do binary addition. That's really simple and straightforward. And you know how to add binary numbers. So this will be the answer. One thing which is interesting here is that if we have this kind of numbers, then we can actually easily convert them to binary with the help of a coder. And then this binary input can be fed to a digital circuit, which may be a binary adder. We will be doing binary adder in our next classes. I mean, in terms of hardware or in terms of circuit. So if this number is fed to one of the input of that binary adder, this number is fed to another input of the binary adder. The binary adder automatically gives you output in this form. So that's really interesting that, okay, this is how by applying electronic circuits, we can do mathematical operations. And that is where this conversion process is very useful. Why useful? Because if you have to enter this number with the help of a simple binary keyboard, which is just containing 0 and 1, it may be a confusing thing. This may not be confusing, but this will be more confusing, right? So doing design hexadecimal based keyboard having 16 keys, and then we convert a particular number to hexadecimal form, which is not that difficult, and then type the that then is converted to binary form, which is then fed to the binary circuit or a digital circuit, binary adder, and then with the help of the circuit they can be added. That's quite very interesting and simple thing. Okay, then how to do subtraction? Again, now I hope you have understood it well, that 2's complement is a very important and very interesting way of doing subtraction. So if you have to do subtraction, basically what we will do is we will be putting the number which has to be subtracted in 2's complement form, and again with the help of that binary keyboard we can enter the number first, then there can be a circuit which can get a 2's complement of a number. So we will be doing all those circuits in detail in our coming classes, that how we can actually convert a number to its 2's complement with the help of a circuit, binary circuit or digital circuit. So this is all. This all is part of coming lectures. Don't worry. But yes, if we use that kind of arithmetic, then we can convert that. How? Okay, we can type 3f. This is quite simple, and this one. Then we can type 5c. So you can design your circuit to be in such a way that if you type minus in your circuit, that minus should mean that whatever number is coming up, it is converted to 2's complement form. So that all can be done with the help of hardware. That's not a very that complicated. So I will be showing it to you in the coming classes how to do that. But okay, once this is done, then 2's complement is there. How we have to find out the answer? Add these two, means this and this binary number is fed to the binary adder, and then this is output of the binary adder. Maybe I should have shown a block diagram for this. Okay, maybe in the next classes I will do that. When we will discuss the hardware component, I will be showing the block diagram of how things are done. Okay, and what is the thing here is, if there is no carry, means the number is negative. I hope you remember that, correct, and is in 2's complement form. So this is 2's complement form. So we have to get the answer. So you can design your circuit in such a way that if you don't get any carry out of a binary adder at the end, then this number is fed again to 2's complement converter, so that the answer then comes in final binary form, which will be nothing but this number. So 1D to the base 16. And this is negative because this is greater. Why greater? You can check what is the decimal equivalent of this. It is straightforward as well. 3 is smaller than 5, right? So even in hexadecimal system, 3 has a lower value, 5 is higher. Correct? And both are appearing at same place. So this is units place. This is 16th place. In decimal case, it is tens place. Units, tens, hundreds, thousands, and so on. So here it is units place. This is 16th place. 16. Isn't it? The weight for this is 16. So means the answer is negative. So that is how even subtraction and addition can be done by using hexadecimal arithmetic in simple manner. You can try some examples like this. I should have given it as an exercise to you, but okay, you do it yourself. So how to subtract binary numbers, I mean hexadecimal numbers rather. So that's what is the procedure is. And here, interesting thing is that this number is greater than this number. So what we have to do, each answer is positive. You can check. Because at the end you are getting a carry. So you have to discard carry. That's the rule of binary addition. Correct? And this number is finally in actual binary form. So you can convert this to binary form. I would be discussing, I mean, we shall be doing much more things during the course. And I'm sure now these kind of examples are inviting your interest. For example, let us think of a circuit which can read the content which are in binary form and display them in hexadecimal form in the form of say 1, 2, 3, 4, 5, 6, so on up to A. So that kind of task is done with the help of decoder. There is something called coder. So a keyboard is a kind of coder because in keyboard you type A, but then there is a corresponding code, binary code for A. So that is done with the help of coder. There is a decoder other way around, means the answer you get is in the form of binary numbers. So these also can be decoded back to your desired number format. Fine. For example, in your keyboard, you have alphabetical keys, you have numbers 1, 2, 3, 4, you have symbols. But interestingly, the actual information processed in your CPU, in your, even your storage system, in your pen drive, all the information is stored in the form of zeros and ones. How is that thing done? That is done with the help of those coder and decoder softwares, which of course interact with the hardware and then accordingly get the data for you. So that is how your digital electronics is really very interesting thing. Here you will be understanding the very deep basics of your computers, that how these zeros and ones are actually interpreted in your computer systems. So with this, I hope today you got help. And that's all for today. Thank you. If there is any question from what we have done today, you can ask. Is there any question or doubt from today? I will be happy to answer because we have time still left. So any question if there is, do ask so that I can try to answer it. Okay, so if there are no more questions, or if there are no questions at all, let me thank you all. One of the student